All right, we're going to look at a pretty difficult silver problem today. That's the USACO 2024 February contest silver problem 2 of test tubes. You can pause the video first and look at the problem yourself. All right, I assume you read the problem. So basically what you're being asked is you're given 2 test tubes and a beaker. And now you have 2 different colors initially in these test tubes, and these colors don't mix. And now you can make some pores between test tubes and beakers, and basically you're trying to separate the colors. And so say you have test tubes being like this, you can first pour the one into the this is test tube 1, this is test tube 2, right? You have color 1 and 2, and then you're trying to separate them so that each test tube only contains one color and the beaker has to be empty in the end. And you're trying to minimize the number of pores that you make, and you also have to output a sequence of pores that you can do to achieve this goal. So you can pause the video and try this problem first. And I will have to say this is really, really difficult. And pardon me for yapping a little bit before actually starting to solve this problem, but this problem is actually really, really traumatizing for me because the contest that it was in was right here. Yeah, 50 points. And as you can see, I only submitted on this problem because it was the only problem that I can actually understand and have some ideas on how to do it. And I got 50 points. So yeah, I was able to come up with a fully urgent solution afterwards, but it still took me a really long time. And this problem specifically, no, this whole contest actually is one of the biggest reasons why I'm so panicked about January contest this year, because all 3 of these problems are extremely difficult, and it's only February. It's not even US Open, and all 3 of these problems are extremely difficult. They all took me 2 hours. Like this problem took me 3 hours. The other 2 each took me 2.5. So this contest, if January appears to be this difficulty, which would not be surprising at all considering that this is last year and only February, if January is this difficulty, I'm gonna get at most 200. So this contest is really scary, and it's the biggest reason why I'm panicking so much about January, and my panics are not unreasonable. All right, that's enough with the yapping. So how do we actually solve this problem though? Well, first of all, we had to make a very important notice that I was actually able to make during the contest, even though I still couldn't solve it. So this notice is that we can combine adjacent colors, adjacent liquids of the same color, adjacent layers. If they're both 2 or both 1, we can combine them. For example, this one can be just combined into 1, 2, 1, and this can be combined into 2, 1. Because, look, when Bessie makes a pour, she moves all liquid of color I at top of one test tube or beaker into another. So if we combine them, it doesn't actually change anything. Like if we pour both of these ones out. So if we just combine them, it just makes our life easier. So that's the first important notice, is to combine them. So now we basically have blocks, right? Every single adjacent block have to have different color. And now we make a second notice, is that we have to make at least the number of blocks pores in order to separate them. Let me put on program, which is said here. So first of all, the first notice is consecutive ones of the same color can be combined, as explained. And after combining the number of blocks is at least how many times we need to pour, because each pour can at most reduce the number of blocks by 1, right? Let me pull out the drawing board. So say we have a test tube. This is test tube 1, that's test tube 2, right? And we have different layers, right? Now I just assume every adjacent layer has different colors. And now say 1, 2, 1, right? 2, 1, 2. And we have a beaker in the middle. Each time we can at most reduce the number of blocks by 1. Say if we pour this one over here, right? And now we have the top is erased. So basically now this is the top and this is the top. We can just pour the 2 into this 2, and now we have one less connected component, because when we pour this into that, we just combine them automatically. And now basically we can just, if we pour that into that, we can just treat it as eliminating this. Or if we pour this into this, we can just treat it as eliminating this one. So basically we reduced the number of blocks by 1. So each pour, optimally, we can reduce the number of blocks after combining by 1, right? And we notice that that's not always the case, because sometimes we can't reduce the number by 1. Like the first pour that we made here. By pouring this 1 into the beaker, which is initially empty, we don't reduce the number of components by 1 because we still have 6 blocks, right? So that's the second type of move in which we don't reduce the number of blocks by 1. And the third type of move, we also don't reduce the number of blocks by 1, is when we pour a color 1 onto a color 2 or a color 2 onto a color 1, right? Because then if we pour the 1 onto 2 over here, well, obviously we still have 6 blocks. So that's the third type of move. So these 3 types of moves are wrote down here. Pouring 1 into 1 or 2 into 2, 1 to 2 or 2 to 1, and then pour either color into an empty container, right? These two does not reduce the number of blocks by 1, and this one does. So basically, you're trying to make as many move 1s as possible so that we can have the minimum number of pours. And actually, we notice that move 2 never happens. It's just intuition. But if you think about it, if you do move 2 to avoid further moves of 3 and 2, you can avoid at most 1 move 3 or move 2, right? Because our goal is to avoid as much of these as possible. You can avoid at most 1 move 3 or move 2, but by avoiding combining 2 containers and resulting in an empty container requiring a move 2 that you can avoid. But the cost saved is the cost of making this move 2, so why would we even make this move 2 in the first place? Okay, so from that we basically prove that we never make move 2s. So basically we have move 1 or move 3 that we can choose from. And now we're trying to minimize the number of move 3s that we make. So this is where this problem gets tough. Like a lot of people can notice this, including myself. I noticed this in the contest. Well, I mean, I didn't actually notice the 3 types of moves, but the difficult part comes here. The solution and I had different approach starting here because my approach is actually, I think, easier because I just did casework, and the solution actually offered a more clever approach in which they actually considered each case and then found that what's optimal to do. Well, I mean, that's kind of also casework, but I'll explain the solution idea later. But my idea is casework. So basically, we have case 1A, 1B, 1C. It's pretty boring, but I'll explain them one by one. So first of all, we notice that only top and bottom actually matters in the beginning, right? Because if we know the top and bottom, since every adjacent block is different, well, obviously we only care about the top and bottom, right? So if we have the same bottom as one case, different bottoms another case, and then when we have same bottom, we have different top, same for different bottom. Okay. This is going to start getting boring. When we have the same bottom, we first notice that for the same bottom, we need at least 2 types of move 3, right? Because if we use the beaker, first of all, we pour it into the beaker, so that's 1 move 3. If you still remember what that is, move 3 in which we don't want. We need at least 1 move 3 to pour into the beaker because it's initially empty. And then, since we have the same bottom, after we empty out one of the containers, we have to pour another different color in. So we have to make a second move 3 because we have to empty one of the containers at least so that we can have each container contains different colors. So we notice that if we use the beaker with case with the same bottom, we have to have at least 2 types of move 3. And when we have the same bottom, we have two different cases. We have different top and same top. And for different top, for convenience, call the 2 with different top and bottom to 1 and the other with 2 because we know one of them have to have different top and bottom and another one have to have the same. And notice that we always want to start with 2 1 because after 2 1 has 1 block left, beaker's top is not equal to 2 1's top and tube 2's top is equal to 2 1's top. So pouring tube 2's into tube 1 now empty tube 2 until finally pour 1 from beaker to 2. And that requires 2 move 3 and that's the best we can do, right? Because we already proved that we can have at least 2 move 2s, 2 move 3s. So when we have different top, we have a strategy here. And then we actually noticed that when we have the same top, it doesn't actually matter because we can just pour one top into another. And now we have situation 1A. And notice that this is a move 1, in which we never make the answer worse by doing a move 1. And after doing a move 1, we convert it into situation 1A, in which we already proved to be the optimal possible for the same bottom. And we notice the same thing when top is not equal to bottom because we can also make just one move. And now we can also convert it into the optimal case of 1A. So this is where things start getting interesting because if we casework different bottom, again, we notice that it's actually also similar because with same top, we can, because for different bottom, we at least make 1 type 3 move. And when we have same top, we have a strategy of only making 1 type 3 move. And we can just convert different top into same top into situation 2A, in which we already proved it's optimal. So basically now we only actually have 2 situations instead of 5 that it looks like we have here. Because for the other 3 situation, we basically just converted into there appears to be 6. For 4 of the 6 situations that we might have, we converted into the other 2 that have been proven to be optimal. So this casework, even though it looks like a lot, It's actually not that much. And I strongly suggest actually looking through this whole thing that will be posted in the comments below. So yeah, we notice that we don't have to prove any of these because they're all optimal. So we actually only need to write a function for 1A and 1,2, the two situations we explained above, to already be optimal for different and same bottom that we already proved. So there's more details obviously for this because this is a really, really difficult silver problem. So I have to probably go through the code. So here, input, obviously, I actually hate multi-test case musical problems. I have to clear so many things. So I just manually memset because I don't trust memset. And we have to know that sometimes we don't use the beaker because all our assumptions above are based on if we use the beaker. So if we don't use the beaker, we just check it. Just treat it as a special case. That's if we don't use a beaker. And if it's same bottom or is it this, or if it's different bottom, we have to treat it differently as we have discussed above with casework. And if it's same top but it's not case 1A, it's case 1B, then we have to convert it into case 1A by doing a type 1 move, and then we call the function same bottom. And that's basically the same for different bottom. We call the function different bottom, diff b literally. And that's actually a bug checker that I use a lot. Like a lot of times, if because CNT is the number of moves that we actually made, and answer is the supposed number of moves that we need to make, because we already know how many moves we need to make. It's just the number of blocks plus 2 if it's the same bottom, and plus 1 if it's different bottom, right? Because we make 2 move 3s for the same bottom and 1 move 3 for different bottom. So we already know answer. And if the actual moves that we make is not equal to answer, well, something must have gone wrong. So my program will output RE. And also, what the frick? Okay, so let's take a look at my same bottom and different bottom function. Same bottom function, obviously, we want to start pouring with the one with different top and bottom, so we swap them. So it makes our life easier. And we start pouring, we make the pour just like I discussed in the casework above. And the same with different bottom. I still strongly suggest looking at this whole code that will be posted in the comments because I have a lot of explanations in it and it's just really, really detailed. So yeah, that's basically how you solve this problem. It's not that difficult because, well, I mean, it is that difficult, but it's not actually that difficult in terms of casework because it looks like there's a lot of cases, but it's actually only 2. And we just have to basically make the first notice of combining consecutive same colors. Secondly, the 3 types of moves that we make. Thirdly, we basically try to minimize the number of move 3s. And finally, we casework. So if you've done those 4 things correctly and you think you have no bugs in your code, you should get this problem right. So yeah, thank you so much for watching. This is a really difficult problem. I would say one more time, probably one of the most difficult ones in Silver I've ever seen. And this contest overall is just so traumatizing. Okay, hope this video helped. Thank you for watching. Okay, it's finally progress report time. That was a really, really long problem analysis, but this is a really hard problem. And I can't help but to miss the back in the good old days of 2018. Before I even started doing USACOs, just look at how easy these problems are. I mocked the USACO 2018 December contest yesterday and the silver of the same contest today, and I was able to solve all 3 of these problems within 2 hours. Actually, within an hour and 40 minutes to be exact. But convention I've already done like a while ago, and Muyo I've also done like 2 years ago. I did both of these 2 years ago, but I don't remember the solution at all. So I basically still came up with a brand new one. And convention 2, I did it probably also a few years ago, but I could not completely solve it. It was basically a brute force that I wrote a while ago. And today I was able to also solve this one within like 40-50 minutes. So convention standard binary search, no special thing to it. And convention 2 is just simulation except with priority queue. And finally, Muyo is DFS plus a tiny bit of brute force, really not much. And yeah, with this contest, like even if I never did any of these problems, I'm confident in getting all 3 of those within 3 hours probably at most. So yeah, why couldn't I be born 6 years earlier? Like I would literally be in platinum because I mocked this one and I was able to basically like get promoted. I was like at like 760, 740. I don't remember the exact score, but I was right around there. So I really like could have gotten promoted easily if I was born like 6 years earlier to platinum. So why is USACO so much harder nowadays? Why can't the 2025 actually January be like the 2018 December instead of the 2024 February? All right. Well, if it's gonna be this difficulty, I really, really, really need to lock in now. I need to be able to AK all of these contests within like an hour or something to be able to get promoted in 2025 January. All right. So that's the progress report. Oh, and also, yeah, I did not actually study for very long because today I did, I'm pretty sure 5 hours, which is quite short, but good enough. All right, lock in tomorrow. Thank you for watching.